I want to show you something called a venturi tube, and here it is. Now, before I explain to you exactly how the venturi tube works, I want to remind you how a barometer works. So a mercury barometer works just basically on the principle of atmospheric pressure. So if you invert a tube full of mercury into a shallow dish full of mercury, the mercury doesn't drain because the region above would then have to be filled with vacuum, not air, right? If the tube was totally filled with mercury before it was inverted, then the region above would become a vacuum if any amount of the mercury were to start to fall, and the pressure in a vacuum is equal to 0. However, the pressure at the bottom is not 0, it's 1 atmosphere. And so that difference in pressure of 0 at the top and 1 atmosphere at the bottom can create enough upward force to account for the weight of the column of the mercury. And in fact, if the column of mercury is exactly 760 millimeters tall, then the difference in pressure would exactly account for the weight of that mercury. So in a venturi tube, we have to consider a couple formulas that you should now be familiar with. One is called the equation of continuity. Area 1 times velocity 1 equals area 2 times velocity number 2. And then we can also express the behavior of a venturi tube in terms of Bernoulli's equation. Pressure at one point plus rho g y1 plus 1/2 rho v1 squared equals pressure at the second point plus rho g y2 plus 1/2 rho v2 squared. Well, a venturi tube is a situation where you have a wide segment of pipe and then a constricted segment of pipe. But the one thing that's the same is they both sit at the same vertical position y. And so we can cancel that out on both sides of the equation for Bernoulli's principle. And then we're left with pressure 1 plus 1/2 rho v1 squared equals pressure 2 plus 1/2 rho v2 squared. So if you take into account both the equation of continuity and this reduced form of Bernoulli's equation, then we can put it all together. We recognize if the fluid is flowing to the right and then gets constricted at point number 2, then the velocity at point number 2 has to be greater than the velocity at point number 1, just based on equation of continuity. But if the velocity at point 2 is greater than the velocity at point 1, what does Bernoulli's equation have to say about that? If velocity number 2 is greater than velocity number 1, the only way this equation can remain balanced is if pressure number 2 is then less than pressure number 1. So we can make an association and say wherever a flow of fluid is constricted and speeds up, that must correspond to lower pressure. And so if we have relatively high pressure in segment 1 where the pipe isn't constricted, then it can support a taller column of fluid in the same sort of way that 1 atmosphere can support 760 millimeters of mercury. Here, in point number 2, where the fluid's moving faster, then that means the pressure has to be less, and so it supports a smaller column of the fluid. And so this is actually a version of a venturi tube known as a venturi meter, in which it's very easy to measure the difference in height at the two tubes, and from that be able to extract the difference in pressures and therefore the difference in speeds. Another demonstration of this venturi effect is to make the fluid that's flowing through the tube air. And then you have an opening here and another opening here. And as the air constricts, it speeds up through the narrow part, slows down again in the wide part. And so the pressure at point 1 and the pressure at point 2 do not agree. There's a velocity number 1 and a velocity number 2. Velocity 2 is greater than velocity 1 just based on the equation of continuity. Therefore, pressure 2 is less than pressure number 1. And so some of the air is supporting this column and actually jets out a little bit. And same thing here. More pressure at point 1, less pressure at point 2. So you put a ping pong ball in this airstream and another one in this airstream, and the ping pong ball is supported at a greater height at position number 1 than it is at position number 2. And if we were in the classroom, I'd probably show you that demonstration live. Groundhogs seem to know something about this venturi effect. So, or actually I think, not groundhogs, I think I'm considering prairie dogs. Prairie dogs always dig their holes underground somewhere near a hill. They'll pile up dirt if they have to make a hill. And let's say somewhere out on the prairie there's scrub brush, more brush over here, brush over here. So as the wind blows across, you have some high wind speed. It's often blocked by these bushes, but if you can pile up one of the entrance holes to the prairie dog's living chambers, then you can expose it to this high velocity, whereas the part that sits down here low is in more stagnant air. So you have fast-moving air near one of the holes and more stagnant air near the other hole. So the whole idea of applying Bernoulli's equation to a venturi tube is to come up with this association that says wherever velocity increases, pressure decreases. And so the fast-moving air represents a region of lower pressure. The stagnant air is high pressure. And so if there's a pressure difference between the two openings to the prairie dog's chamber, air will continuously circulate through. And so it's a form of prairie dog air conditioning. What are some other examples of this venturi effect? It can be seen in the design of all plumbing drain systems. So this is actually a poor example of a plumbing system. So if you had, well, first of all, why do they always put these U-shaped traps wherever there's a drain? The toilet bowl itself has a U-trap built into the porcelain of the bowl. There's another U-trap at the washing machine. Well, the point of that is to keep the bad-smelling vapors that would come in the wastewater from being able to make its way into the home. We don't want these drain water vapors to come out, right? Especially if the toilet is part of our water that's going to be draining. So how do they do that? Well, let's see. Whenever you run the sink or flush the toilet or run the washing machine, water sits in this U-trap, and then the water becomes a barrier to these vapors. There's a problem with this. When the water flows, now you have fluid in motion, and again, as velocity increases, pressure decreases, and so on this side of the U-trap, the pressure is 1 atmosphere, right? Because it's just opened up. And then on the other side of the trap, the pressure would be less than 1 atmosphere. And so that difference in pressure would push the fluid out of the U-trap, and then that barrier would no longer exist, and you'd be able to smell the bad vapors coming off of the drain water. So in order to make sure that there's no pressure difference across the U-trap, a better design would be to extend the drain pipe vertically so that it punches through the roof of the house and opens up to the atmosphere here. So now the pressure on both sides of the trap, here is 1 atmosphere, and this is also open up to 1 atmosphere, and without a difference in pressure, the water stays in the trap and maintains that vapor barrier. And so that's the rationale why this would be not a preferred way to breathe, but if, maybe you were trapped in a high-rise building in the case of fire. Most deaths from fire don't come from being burned, but from inhaling smoke. And so to save lives and prevent death from smoke inhalation, there's actually a company that manufactures these breathing tubes that are meant to be pushed through your toilet, and you push it far enough that it goes beyond the U-trap and then to the other side. And after you've flushed and wait a moment, all the water has drained out. But if it's been a well-designed system, then that drain pipe leads all the way up and out of the roof, and then you have access to fresh air, and you don't succumb to the danger of smoke inhalation. I think there's a story that goes something like this. Everybody has a neighbor whose cousin had a best friend who was standing too close to the train tracks when the train came rolling through the station, and in the wake of this fast-moving train, then there's a region of low pressure. As velocity goes up, pressure goes down, and so that fast-moving wake of air creates a region of low pressure that then sucks the person into the tracks. Although nothing sucks in physics, I think a better way to say it would be the rest of the atmosphere pushes the person. I just don't think that difference in pressure could ever be great enough in magnitude to account for the mass of this person. But in principle, I understand the idea. Now, a shower curtain has a lot less mass, and when water flows at high speeds, it creates this wake of fast-moving air that moves along with it, and that becomes a region of low pressure. But the rest of your bathroom, outside of the shower, is stagnant air that's relatively higher pressure of 1 atmosphere. And so you've probably noticed that if you have a thin shower curtain, that it often seems to get sucked into the shower. But once again, nothing sucks in physics. What we mean to say is the atmosphere is able to push the shower curtain inward, and you do everything you can to try to escape the attacking shower curtain. So you've probably seen a lot of examples of this principle that says wherever fluids move fast, you have high pressure. Some people wherever fluids move fast, you have low pressure, and some people try to argue that this is the one and only reason that airplane wings have lift. So let's draw a basic shape of an airplane wing, that general airfoil shape. A lot of curvature on the top surface of the wing, not as much curvature on the bottom, so it's somewhat of this teardrop shape. And then the plane's moving with a velocity, we'll say, to the left. Now, when a plane is taking off, the reason it gets lift has to do with angle of attack. So if you think about Newton's third law, as the plane moves this way, it has a horizontal component of velocity. And so velocity is relative. We can either say the plane is moving through the air, or the air molecules are approaching the wing, and an air molecule hits the wing, and then if it's at a 45-degree angle, applies a force, and the air molecules bounce down vertically in this direction. And by Newton's third law, if the wing pushes the air down, then the air pushes the wing up. So when the plane has an angle of attack, it's really just Newton's third law and the force of collision between the wing and the air molecules that gives it lift. But once the plane reaches a cruising altitude, there's no longer the angle of attack, so there's no longer a collision between the air molecules and the bottom side of the wing to provide lift. So the lift has to be explained in some other way. So let's imagine 2 air molecules, and again, velocity is relative. We can think of it as the plane is moving to the left, or we can think of it as the air molecules have to move to the right, and maybe one air molecule passes over the top of the wing, and another one goes over the bottom of the wing. Well, the one that passes over the top of the wing travels a slightly greater distance because the wing has a curvature over the top, whereas the distance along the bottom is more of a straight line. So here's the thing. If there's a guarantee that the 2 air molecules reach the other side of the wing in the same amount of time, then the velocity at the top had to be a greater velocity, and the velocity of air at the bottom was slightly lesser velocity. And if high velocity means low pressure, and less velocity means higher pressure, then you can see how the difference in pressure can create the lift. There's a little more to it than this. Actually, the 2 air molecules that start together as the plane approaches them, do not reach the other side of the plane in the same amount of time. In fact, the one that goes over the top takes less time. So it doesn't just go faster because of the shape of the wing. It actually gets there, it travels a greater distance and in less time. So it goes significantly faster over the top of the wing. And the reason it goes faster over the top has to do with something known as the Magnus effect. And I'll link another video on the Magnus effect for you to explore that phenomenon. However, we can say with certainty that Bernoulli's equation does factor in somewhat to the lift of the airplane wing, because there definitely is a pressure difference between the top and bottom surface as the plane cuts through the air. So this diagram oversimplifies things and suggests that Bernoulli's principle is the only factor that plays into the lift of an airplane wing, but there's simply more to it than that.